For today's video, we're going to be talking some more about linear transformations. And for today, we're going to look at a problem in section 2.8, question number 91. And this asks us to prove that the composition of two one-to-one linear transformations is also one-to-one, and if the result would be the same if the transformation was not linear. So before we get started, let's talk about definitions. What do all these different words mean? Because there's a lot in here, right? Well, first let's just say, what is a function? So a function is just some rule that's going to take one vector in our domain and assign it to another unique vector in our codomain. And the vector that it's assigned to in the codomain, we call that the image. And for this example, we're going to be calling the codomain S1 and we'll be calling the domain S1 and the codomain S2. Okay, so a linear transformation, it's just a function, right? It's going to map a vector from one subset of a vector space to another, and it's going to be preserving vector addition and scalar multiplication. Remember that from our last video. And here I've listed the formula we would use to prove that something was a linear transformation and does maintain, preserve both of those properties for any vectors in our domain and for any scalars in the real numbers. So here's just a description of what exactly this linear transformation is doing, right? So we're going to start with a vector in our domain S1. We're going to apply our linear transformation, and we're going to end up with a vector in our codomain of S2. So what does it mean if that function or that linear transformation is injective? Okay, so that's what we call if it is one-to-one. It's an injective function. So then if we had two vectors in our domain and what they mapped to in the codomain, if they map to the same place in the codomain, if it's one-to-one, we know that the only way that can happen is if those two original vectors are equal. So in other words, if two vectors are mapping to two different places in the codomain, those are not one-to-one. Those are not injective function. That's not an injective function. So the next thing that's going to be mentioned in our problem today is that we're dealing with the composition of linear transformations. So we actually have two different linear transformations there. And we have, say we started with F. That would go from the domain S1 to the codomain S2, and we have another function that starts the domain of that. If the domain of that function is the codomain of the other function, we can actually combine those. We can get the composition. We'll call it G of F, and that would be a transformation now that would go from S1 all the way to S3, and we would denote that as G of F of V. And this would be for all vectors in our original domain of S1. And that's going to look something like this. And essentially, we're just combining these. We're doing the same thing. We're doing them both at the same time. So instead of having a transformation of F and then a transformation of G, we just call it the transformation G of F. And we start in the domain of S1, and we map to the codomain of S3. So now that we have that background and those definitions, let's take a look at our actual proof of our problem today and see if we can work through it now. And like always, we're going to start with the information and the assumptions that were given in the problem. So we want to start with two linear transformations that are both injective. So we're going to say T goes from the domain of Rn to the codomain of Rm, and then our second transformation, U, will go from the domain of Rm to the domain of the codomain Rp. And we are given that these are both injective linear transformations. These are injective functions. So our composition U of t would go from Rn to Rp. Okay, so we're going to start with two vectors in our domain of Rn, and we're going to set that equal to so that U of t of U is equal to U of t of V. That's because we're trying to prove that this is injective. So just by the definition of a composition, that means that U of t of U is equal to U of t of V. Now, we are given in the problem that U is injective. So we know that everything inside of the inside of those parentheses must be equal since it's already given that it's injective. So T of U must be equal to T of V. And we're also given that T is injective, so we know that anything inside of T must be equal. So we now know that U must be equal to V. Well, since U is equal to V, and what we started with is U of T is equal to U of T of V, then we know now that the composition of U of T must also be injective. Now, in this proof, we didn't do this specifically. We didn't specifically say that this was a linear transformation, and that's because this is true for any injective functions. So for the second part of this problem that asks would it be true for a nonlinear transformation, the answer is yes, because in this case, since it's true for all injective functions, it doesn't matter if this is a linear transformation or a nonlinear transformation. The results are going to be the same.